Any general questions or problems? Anything? You good to go? Nothing in the chat. So back to what we were talking about. Again, we were talking strictly about van der Waal forces. And the issue here, which is really in some sense one of two critically important things about the van der Waal forces, is that they scale with size, right? It's technically number of electrons. That's also the same as molar mass. So you can use either metric, but as the molecule gets bigger, the van der Waal forces get larger. Okay. This is critically important because this is the only one of the intermolecular forces that is true of. And you'll see what I mean in a minute, right? The other big thing about the van der Waal forces is simply the method by which they occur, right? Which is I have this temporary instantaneous dipole that forms, which influences an opposite and therefore attractive dipole in a neighboring molecule. Again, as long as that neighboring molecule is close enough to feel the charge separation, okay? This is the thing that is universally true of all of my intermolecular forces. And so before we get to all the fancy things you can do with it, and again, we're going to assess them in a somewhat indirect way relative to phase. And this is kind of where we left off on Wednesday, right? The intermolecular forces between two molecules don't change in magnitude, right? If you're two water molecules, you always like each other exactly the same much amount, right? That's something of an ensemble average, by the way, because of course, you know, they could be different distances apart. But if you take two water molecules at a given distance, they always like each other exactly the same amount, right? They don't know or care whether they are solid, liquid, or gas, right? What makes them solid, liquid, or gas is whether or not that force of attraction is strong enough, right, to change the way the molecules are moving, right? Solids are stuck more than liquids, which are stuck more than gases, although technically there's no difference in the intermolecular forces in those three different phases, right? What's different is how fast they're moving relative to those intermolecular forces. And so we'll talk a little bit later about phase in general, right? But there's always this balance between kinetic energy and pressure as sort of the molecules trying to move and escape, and the intermolecular forces, which because they're always attractive, are always trying to hold the molecules together, right? And so in the end, we end up with using phase changes, and specifically phase change temperatures, as a way to assess the strength of the intermolecular forces, right? And again, my continuing theme, right? The molecules are moving except at 0 Kelvin, right? And so, right, my phase change is driven not by a change in the intermolecular forces, but typically, because we don't change pressure as readily as we change temperature, typically my phase changes occur as a result of a temperature change because I've added energy, right? Specifically kinetic energy, which causes the molecules to move faster, right? If that is enough for them to overcome the attraction to the other molecules in the system, they are free of the other molecules. And so you go from solid to liquid to gas, depending on how free you are, right? If you turn off the motion, right, the molecules are attracted, they're just going to clump up. If they're moving quickly, or at least quickly enough, they escape each other, right? The maximum attraction between these two pentane molecules is this alignment, right? Where you've got complete overlap of the one caterpillar with the other caterpillar, right? Because they're moving, they're not always stuck, depending on how hot or cold they are. If they're moving, because again, they're always moving. This is my best attempt to give you a non-static picture, right? If they're moving slow enough, they're still moving, but not quickly enough to escape the intermolecular forces. So in this case, it's a solid, right? And they're sort of moving relative to each other, but they can't escape each other. Right. And so we'll talk much more about phase changes in a second. I do want to run through the other types of intermolecular forces. And frankly, if you understand the van der Waal forces, they're all the same. The only difference, well, there's really two differences, is that my bucket is no longer level, right? And this different type of intermolecular force is very local, right? If I start with a diatomic, the distinction between local and global isn't obvious, but this is the difference between what's usually termed a dipole-dipole interaction, right, and a van der Waal force. Instead of bromine, the molecule, I now have hydrogen bromide, the molecule, right? Whereas if it's two bromine atoms, the bond is completely nonpolar. If I have hydrogen, right, the bond is polar, which means the electrons are always leaning toward the more electronegative element, which in this case is bromine, right? And so I no longer have a quote unquote instantaneous dipole like I did with the van der Waal interaction. There is always a dipole there. And so it's permanent. Okay. And so as you can see, right, since in this case I have two hydrogen bromides, they are both polar molecules. They both have a permanent dipole, right? And therefore there's none of this flashing on and off of that dipole. And so again, I have an opposite and therefore attractive permanent dipole interaction between these two molecules. It might seem like that means you could be repulsive. But again, here's where the case of being mobile matters, right? These are not two molecules that I plopped down on the screen this distance apart like I did when I drew this, right? These are molecules that are moving, right? And so again, the interaction is based on them moving close enough together to feel each other. And so if this molecule, say the top molecule, is moving towards the bottom one, right, it is not going to approach it in this orientation because there's a natural repulsion between the positives and a natural repulsion between the negatives, right? And so as this molecule approaches the other one, it's going to naturally rotate so that the positive side of the molecule is near the negative side of the neighbor, right? And so still, even in the case of having a permanent dipole, all of my interactions are attractive. Okay, and so there's 2 points to make about this. Well, maybe 3. One's not really a point so much as just an emphasis, right? This is no different in terms of the nature of the interaction of the van der Waal force, other than the fact that the dipole is always there, right? The electron cloud is, however, still sloshing around. So even if I have a permanent dipole, I also have a van der Waal interaction, right? And so, you know, if you like my metaphor, here it is again, right? A van der Waal interaction is like water sloshing in a bucket. And so sometimes it's up on the left and sometimes it's up on the right. And that's my instantaneous dipole. If I have a permanent dipole, it's kind of like my bucket is on a slope, right? It's always up a little bit on one side, but it's still sloshing. And so there's 2 sets of dipoles here, right? My permanent dipole and my instantaneous dipole. All right.
Question.
Yep.
Does this mean that permanent dipole, like polar molecules, tend to form crystals because their dipoles would have to be arranged in such a way to always attract each other?
Well, I mean, yes, but that's not unique to polar molecules. The question, for those of you in the room, was the polar molecules tend to form crystals because of the dipole, right? But again, whether it's a polar molecule or not, there is an attraction between it based either on van der Waal forces or dipoles or both. And so all materials have a tendency to align themselves to maximize their intermolecular forces. And so they all kind of form crystals. What it will change is the temperature at which that happens. Does that make sense?
Yes.
Right. Which brings me really to the second point I want to make about dipole-dipole interactions. These are stronger than the van der Waal. I have a permanent dipole there. It's not flashing on and off, right? And so if I'm talking about a molecule like HBr, its intermolecular forces are dominated by the dipole-dipole interaction, although it does have both, right? But there's an important corollary here, which we'll see examples of in a little bit, right? This is local. Even in a bigger molecule, right? It's my bond that's polar. And so it's only this bond that has a dipole-dipole interaction with the similar polar bond on the neighboring molecule. If I've got a much bigger, I hate to flash ahead because people hate it, but I do have pictures later. If I have a much bigger molecule, I forgot how far I had to flash ahead, right? If I have a much bigger molecule like this, that's a chlorine on the end, right, of one of my caterpillars, this whole part of the molecule here is nonpolar. This whole part of the molecule here is nonpolar. My van der Waal force is over the entire molecule, whereas the dipole-dipole interaction can only exist where the polar bond is, right? And so you end up here with a choice. If the dipole-dipole is going to manifest itself, this is the only orientation that will do it, right? On the other hand, and we'll get to this a little bit later, if the van der Waal force is going to maximize itself, they need to align that way so that the molecule is aligned with the whole molecule. And so this molecule is technically polar, but as you will see in a zillion slides. I flash forward, what, about 40 slides, right? This molecule is actually dominated by the van der Waal forces, not the dipole-dipole, because the dipole-dipole is stronger at that locality, right? But it's not global. And if you start adding them up over big molecules, the weaker force has a cumulative effect, which is larger. Right. And so really, that is ultimately the only difference between all of my other forces and the van der Waal forces, right? If I've got a polar bond, it's technically a dipole-dipole on top of a van der Waal, right? If that polar bond is really, really polar, I have what is called a hydrogen bond. But again, it's really just an extra strong dipole-dipole interaction. So it's still the interaction between two molecules that have a polar bond. It's just an especially polar bond, right? This is really a very limited set of bonds. As the name implies, there has to be a hydrogen, right? But it has to be a hydrogen that's bonded only to either fluorine, oxygen, or nitrogen. If my hydrogen is bonded to any other element, I don't get hydrogen bonding, right? And the reason is twofold. There's an electronegativity difference. Fluorine, oxygen, and nitrogen are highly electronegative, although so is bromine. And so electronegativity is is necessary, but not sufficient, because I also have a size issue. Fluorine, oxygen, and nitrogen are similar in size to hydrogen. Bromine is much bigger, right? And so it's a very, very limited set of bonds that display hydrogen bonding. As I like to remember it, or as I like to try to get you to remember it, hydrogen bonding is fun, F-O-N, right? Or I guess you could call it phone. Hydrogen bonding calls you on the phone. I don't know, right? But it has to be hydrogen bonded to a fluorine, oxygen, or nitrogen because of the size issue. It's just an extra big dipole. Hydrogen, not very electronegative. Oxygen, very electronegative. So it's really just a bigger dipole than other polar bonds, right? And you can see how strong this is if you compare two very, very similar molecules, one of which has hydrogen bonding and one of which doesn't, right? H2O and H2S, sulfur is right under oxygen on the periodic table. So the bonding of both of these ends up being the same. They're both, if you want a Lewis structure, they're both bent. One has the sulfur in the middle, the other has the oxygen in the middle. Hydrogen and sulfur, not as polar as hydrogen and oxygen, but also sulfur much larger than oxygen, right? And so if you look at these two molecules, H2S is twice as massive as H2O, right? So based on van der Waal forces, hydrogen sulfide should have stronger van der Waal forces and therefore a higher boiling point or melting point, right? And it's twice as big. There's a significant size difference, right? But if you look up the boiling point of those two compounds, water boils, as you probably know, at 100 degrees Celsius or 373 kelvins normally, whereas the boiling point of H2S is 213, right? That is all because of the hydrogen bonding, right? The van der Waal forces actually favor the H2S but the hydrogen bonding is so strong, right? The water ends up with what is sometimes referred to as an unnaturally high boiling point. I'm not a big fan of that phrase, but right, it actually has a naturally high boiling point because, hey, it hydrogen bonds, right? But again, it's an electronegativity difference, right, that makes it polar, but it's the size difference that really maximizes the polarity, right? If you look, right, fluorine, oxygen, and nitrogen are very electronegative, but quite frankly, chlorine is as electronegative as nitrogen, and bromine is almost as electronegative as nitrogen. Yet the size difference makes it impossible to get what we're terming hydrogen bonding. This is to scale, right? The modeling of an HO bond, right? This is not me arbitrarily using circles. I actually use software to calculate the size of these things, right? And you'll notice oxygen is bigger than hydrogen. Hydrogen is tiny, but it's similar in size. You know, it's maybe twice as big or so, right? Chlorine, remember, again, is as electronegative as the nitrogen, but this is hydrogen chloride to scale. Right? It's a beach ball with a pimple. It's still technically a polar bond. It is technically as polar a bond as hydrogen-nitrogen would be. The problem is, if you have an OH bond, you can easily overlap the dipole. And remember, that's where my intermolecular force comes from. It's the dipole of the two neighboring molecules overlapping in opposite orientation. There's no way to do that with HCl, right? It's just round. There's a tiny, tiny dipole there, but there's no, I shouldn't say there's a tiny dipole. There's a significant dipole there, but it's tiny in size, right? And buried in the chlorine electron cloud. No matter how I align those, the hydrogens always end up closer to each other than the chlorines. And so there's no way for me to get the relatively positive hydrogen over the relatively negative chlorine, right? I really somehow want the hydrogen to be over here at the same time as I want this chlorine to be over here, but it just doesn't work spatially, right? And so the only atoms that are small enough to allow this to happen, because hydrogen itself is pretty small, are fluorine, oxygen, and nitrogen. So it's a very limited set of bonds. Yes, no on that? Right. And so if I have a nonpolar molecule, I only have van der Waals forces. Right. If I have a polar bond, I can also have a dipole-dipole. If it's a special kind of polar bond, I call it a hydrogen bond. If I go to an extreme polarity, right, I no longer call these polar bonds if the polarity is extreme. I call it ionic. As you might recall, right, the definition was electronegativity difference of greater than 1.9. Right, and so I now have an extreme slope for my electron bucket, so extreme that I don't simply have charge leaning one way, right? It's all but moved over, right? Sodium has given, for all intents and purposes, one of its electrons to the chlorine. So chlorine has a full negative charge, not just a little extra negative character, leaving the sodium with a full positive charge, right? These are extremely strong forces. Again, in some sense, it arises from the same genesis of any of my other forces, but the charge separation is so extreme, right, that in fact there's no distinction here virtually between the intermolecular force and the bond, right? Especially as drawn, right? Why does this sodium like this chlorine any better than it likes this chlorine? The fact is it probably doesn't if the distance is the same, right? And so ionic intermolecular forces are incredibly strong. They're the same order of magnitude really as the ionic bond, right? This is the reason, and this is a common and constant refrain this entire semester, right? That I say ionic compounds are not molecular. That is critically important. We talked about it a little bit in the fall. If you were there in the fall, ionic compounds, when they dissolve, anyone? I'm going to say it like 1,000 times this spring. This is only the first time. Ionic compounds, when they dissolve, they dissociate, right? They're not really bonded, right? What I have is a whole bunch of ions that cling together because of this electrostatic interaction, opposites attract. But there's also no ownership there. That bottom sodium is not really bonded to that bottom chlorine any more than it's bonded to the chlorine at the top. It's just kind of stuck to both of them because they're oppositely charged. And in fact, if I drew more of my sodium chlorides in this picture, that sodium is probably associated with as many as 6 chloride ions, because you could also put a chloride out here, right, towards me, or in the back plane, or you could put another chlorine over here, or another chloride over here. Right, and again, it partly depends on size and whatever, how many I could get clustered around there. But there's no reason for the sodium to be considered married to any one of those chlorides. It's just kind of stuck to all of them. Right? And so ionic compounds ultimately behave very differently than molecular compounds. Right? If you're glucose, the carbons are all bonded to other carbons and to hydrogens. Right? And there's more to this molecule, but who has time? Right? There's actual ownership there. That carbon is always associated with the carbon next to it and the hydrogen above it, whether it's dissolved, whether it's a solid, a liquid, or a gas. Right? Ionic compounds are fundamentally different because the ions aren't really bonded in any permanent way to their neighbors. They're all just sort of stuck together because of charge. And I will harp on that constantly all semester because we have a lot of ionic compounds. All right, this is by far the strongest possible interaction. Right? One of the easiest things to say definitively in this entire subject, right, is the ionic compounds, the ionic interaction trumps everything. Right? And you'll see what I mean in a minute when we go through some melting points and boiling points. It's worth pointing out that in theory, you could mix and match these, right? Up till now, I kept drawing all the molecules as being pairs of the same molecule. But if I have a nonpolar molecule mixed with a polar molecule, my interactions can also be mixed, right? So instead of just a van der Waal force or just a dipole-dipole interaction, I can have a dipole-induced dipole interaction. I could have an ionic dipole interaction, right? Or even an ionic induced dipole. So if I mix molecules, I could also mix the forces. Although for the most part, we'll stick to pure substances, at least for a while, right? And so basically, if I leave out the mixed forces for the moment, I have 4 similar forces. They're all dipole interactions, right? The bottom three are based on permanent dipoles and really just differ in the degree of the dipole, right? Hydrogen bond is just a bigger dipole than what I'm calling a dipole-dipole interaction. It almost really should be 2A rather than 3, right? And the ionic force is just a dipole that is so extreme that I actually have charge separation, right? If you think of it in terms of electronegativity difference, which is how we talked about polar bonds, you know, I go from 0 for bromine-bromine, right, through up to 0.4 is usually considered nonpolar. And then I have those polar covalent bonds until I get to an electronegativity difference of 1.9 or greater when it's considered ionic. In some sense, it's really a continuum, right? But we do tend to think of the ionic bonds as being discrete from the polar covalent. Right. The van der Waal force, again, is based on a temporary dipole, unlike the other three. But again, the biggest difference, right, for the van der Waal force is it's the only one of them that's global, right? It's the whole bucket of electrons sloshing around. The other ones are based on the polarity of individual bonds. And so they tend to express themselves locally, which you'll see if we look at a bunch of molecules here. Right. So first, just to emphasize my ionic bonds, I present you with sodium fluoride and fluorine. Right. Sodium fluoride is ionic, right? It's a metal nonmetal. Sodium is what, 1.9, I think, for electron negativity versus 4 for fluorine. Right. Fluorine is actually a gas at room temperature. Right. They're actually similar in size. Right. In fact, the molar mass, very similar, 42 and 38. They're in the same row in the periodic table. Fluorine, a little bit smaller than sodium, but not a lot. Right. And so those molecules, very, very similar in size. You would expect them to have very similar van der Waal forces. They're both diatomics, so they're little bar-shaped molecules. Right. But if you look up the boiling point and melting point, sodium fluoride melts at 1266 Kelvin, right? Fluorine melts at 53 Kelvin, right? That's a factor of 20 to 25, right? That is all the ionic interaction, right? The van der Waal forces for those two molecules should be similar. That entire difference in melting point and boiling point gives you an idea of the magnitude of the difference in strength of those two forces, right? And you see a similar roughly 20 to 25 factor in the boiling point, right? Because again, my phase transition temperatures can be viewed as a proxy for the strength of the intermolecular forces, right? Because that's what makes the phase transition happen. I have enough kinetic energy to escape the intermolecular forces, which otherwise would make all the molecules cling together because they all like each other, right? But you're only a solid if you like each other more than you want to escape each other with your kinetic energy, right? And so I know of no better way to emphasize the difference in strength between ionic interactions, right, and my van der Waal forces. And so, you know, you can play this game with a lot of molecules. Here's another pair of diatomics. Both of them are gases at room temperature, right? Hydrogen bromide was, in fact, my example of a polar molecule. Chlorine, of course, is nonpolar. It's a chlorine bonded to a chlorine. The size difference is not extreme. Right, hydrogen bromide is slightly heavier than chlorine, right? And so in terms of van der Waal forces, I expect hydrogen bromide to be slightly stronger, right? Hydrogen bromide is polar, chloride isn't. So I also have a dipole-dipole interaction, right? And so everything favors hydrogen bromide having the stronger intermolecular forces, right? It's slightly heavier. Again, you know, they're relatively equal, so that wouldn't be a huge difference, but it does favor HBr, right? And HBr does have a dipole-dipole, which chlorine lacks. That definitely favors chlorine. And I said, and I wasn't lying, that the dipole-dipole interaction is generally speaking stronger than the van der Waal force, at least over that single bond. And these are little diatomic molecules. So everything says HBr should have the higher boiling point. So of course, turns out chlorine does. Now they're close. All right. But everything says HBr should have the higher boiling point, yet chlorine does by a little bit. This is my caveat slide. So welcome to the caveat, right? My hand-waving arguments based on size and polarity leave out the actual molecular structure issue, right? And geometry does matter, right? Because even though technically speaking that dipole might be strong, it can only manifest its strength if it overlaps with the neighboring dipole, right? And this is, again, the issue we had with the hydrogen bonding. That's HBr to scale. It's almost a perfectly round molecule. So again, there's no way to overlap my dipole. There's not even a good way to get the van der Waal force to manifest itself because it can't easily overlap the molecule, right? Whereas chlorine, because they're both chlorines, looks exactly like that. It's a little bar-shaped molecule. So if you go to overlap them, right, it is much easier to overlap the two little bar-shaped molecules than it is to overlap the beach ball. Right. And so, as I say, this is sort of my caveat pair of compounds, right? My hand-waving arguments works great, right? If my molecular structures are very, very similar, right? That means both size and shape, right? That's why the alkanes work so well. They're all just little caterpillar-shaped molecules, right? If my molecules have either very different shapes or potentially very different sizes giving rise to different shapes, right, my hand-waving arguments fall apart, right? If I actually compare bromine, the molecule, to chlorine, the molecule, now my argument about van der Waal forces works perfectly, right? Bromine is much bigger molar mass-wise than chlorine. It should have stronger van der Waal forces. They're both nonpolar. They're also both shaped the same, right? They're both bar-shaped molecules. One's a bigger bar than the other, but they're both bars, so it's easy to overlap them. And now my hand-waving argument works perfectly. Bromine, the much larger molecule, right, boils at 332 kelvins, whereas chlorine boils at 239 kelvins. Right. But underlying my comparison of van der Waal forces is also the fact that these molecules are similarly shaped. And that's why it's very, very hard to really do this quantitatively, right? I can make hand-waving arguments about what should be more or less in boiling point, right? But again, to whatever extent size or shape are radically different, that can really undermine my hand-waving arguments. And I would have a really hard, you can calculate these things, don't get me wrong, but it's not a simple calculation here. And so I really would not have necessarily guessed, right, it bromine being 50% higher in boiling point than chlorine, right? And so my hand-waving argument, you know, on the homework, in the class is really more about this should have a higher boiling point because of, in this case, van der Waal forces, but I can't easily quantify it. And as HBr and chlorine point out, if the molecules are too different in shape, it's easy to be wrong, or maybe hard to make the hand-waving argument, right? And so here's a bunch of compounds, and you can see what I mean about some of these things. So there's our friend water, right? Again, water hydrogen bonds. And again, if you compare it to its much bigger friends here in the table, right, you can see how big an effect the hydrogen bonding has, right? Water boils at 373 Kelvin. It's actually the highest molecule in that table except for the ionic one, right? Even though it is by far the smallest one. The only thing that's even close in size is propane. It's only 2.5 times as big, right? And yet water's boiling point, you know, is about 1.5 times, well, actually a little more than 1.5 times what the boiling point of propane is, right? And so those hydrogen bonds are strong. You can also see here how relatively unimportant simple dipole-dipole interactions could be, right? For example, if you look at sulfur dioxide, right, which is a polar molecule that weighs about 64 grams per mole, and you look at chlorine, which is nonpolar and slightly heavier, right, you can see the polar nature of sulfur dioxide having an effect, right? It should have a boiling point that's less. It's now slightly more. Right. But that effect doesn't overcome the van der Waal issue if you look at something like hexane, right? Hexane is perfectly nonpolar, right? It's 30% bigger than sulfur dioxide, and it now has a significantly bigger boiling point, even though there's no dipole, right? And that again gets to the fact that my van der Waal forces, because they're global, continue to grow with the size of the molecule, whereas my dipole-dipole interaction is always local, and it only involves the bond that is polar. And so sulfur dioxide is a triatomic, 1 sulfur, 2 oxygens, right? It compares well with water, which is also triatomic, right? Although their size difference is significant, right? But if you look at hexane or chloropropane, right, which are bigger, right, the cumulative effect of the van der Waal forces is now actually greater than the dipole-dipole, which is why I sometimes say that my dipole interaction, not my hydrogen bond, because that's sort of in a class by itself, but my dipole interaction is something of a tiebreaker. If I have two similarly sized molecules, one of which is polar and one of which is nonpolar, right, I expect the polar one to have stronger overall intermolecular forces, right? But if I've got significantly different size to the molecule, that local dipole-dipole interaction often doesn't matter at all. You can sort of see this, right, if you compare chloropropane to propane and to hexane, right? Chloropropane is a slightly shorter version of this, right? It's a 3-segment caterpillar with a chlorine on the end. And again, the only polar bond is the carbon-chlorine bond on the end, right? And so if you look at chloropropane and propane, there's a significant difference, but there's also a significant mass difference. And if you look at hexane, which is also nonpolar, but of similar size to chloropropane, right, it actually has a higher boiling point because, again, there is not any good way to both maximize my dipole-dipole interaction and my van der Waal. And if the molecule's big enough, the cumulative effect of the van der Waal forces, even though individually they may be smaller, over the course of the whole molecule, it ends up being bigger, right? Whereas something like water, right, water's quote unquote unnaturally high boiling point is partly due to the hydrogen bonding. It's also due to the way you could stack the molecules, right? In fact, you have two polar bonds that you can easily stack with two neighbors. And because it's only a triatomic, there's no bigger van der Waal interaction that I need to try to maximize. Even a hydrogen bond on the end of a large molecule won't do anything significant to the boiling point. For example, right, if you look at octane and ethanol, right, octane is much bigger than ethanol, but ethanol hydrogen bonds, right? Now, based on van der Waal forces alone, I expect octane to be higher. But ethanol hydrogen bonds, right? And hydrogen bonding is stronger, yes, but it's local. In fact, ethanol has a lower boiling point than water, even though it also hydrogen bonds, and even though it's bigger than water. Why? Because, again, I now have a caterpillar with a hydrogen bond on the end. I either get the van der Waal forces or the hydrogen bond. I don't get both. And unlike water, which has two, I can't stack it so nicely. And so the hydrogen bond is definitely having an effect here, right? Because octane is almost 3 times the size of ethanol. Without the hydrogen bond, I would expect there to be a much bigger difference in boiling point, right? But that hydrogen bond, even though it's stronger, right, isn't enough to overcome the cumulative effect of size, right? And in fact, if you look at two big molecules, one of which hydrogen bonds and one of which doesn't, right, octane and octanol, yes, the hydrogen bond has an effect, right? But it's not this outsized effect that you see with the tiny water molecule, right? And we're just about out of time, so you see a much bigger effect with a smaller molecule with a hydrogen bond, right? Here's ethane and ethanol, right? Again, caterpillar with a hydrogen bond on the end versus caterpillar without one. Now there's a gigantic factor of almost 2 difference in boiling point, whereas for the octane and octanol, yes, the hydrogen bond is helping, right? But it's a marginal effect. I'm only 15% larger in boiling point because, again, much of that is now due to the van der Waal forces, which are the same for those 2 molecules. Whereas here, the van der Waal forces might be similar, but the hydrogen bond is a much bigger portion of the overall molecule. Right? And so the bottom line is I am most confident if I'm making this comparison based on molecules that are similar in size and shape, right? It is really, really hard. I mean, I looked up the boiling points here, obviously, to tell how big my caterpillar has to be before the cumulative effect of the van der Waal forces are greater than the hydrogen bonding. I mean, it's also worth noting, while we were comparing things, octane has a higher boiling point than water, right? Even though it's completely nonpolar, and water has a double hydrogen bond, right? But now my cumulative effect of the van der Waal force is even greater than the hydrogen bonding, right? And so, you know, if I'm comparing ethanol to octane, hard to say for sure. One has a whole lot of van der Waal forces, one has a little hydrogen bond. Which one's bigger? I'm not 100% confident, other than I looked it up on Wikipedia, right? HBr and Cl2, as we saw, because of the shape difference, they don't overlap very well. And so the size and the polarity fool me, right? Whereas if I'm comparing the caterpillars, they're all caterpillar shaped and the comparisons are easy to make, right? Propane is higher than ethane is higher than methane, right? So in general, the only thing I can say with 100% confidence is if it's ionic, it has a gigantic boiling point or melting point, right? Because the ions are virtually bonded to all their neighbors. Hydrogen bonding and dipole-dipole interactions are significant, but their significance decreases as the molecules get bigger, right? Because van der Waal forces grow with size. Hydrogen bonds and dipole-dipole interactions are only over that single bond length. And so they're always kind of the same size. All right. And again, the bottom line, which carries over into Monday when we'll talk more about phase changes, right? My melting points and boiling points, right, regardless of what the forces behind them are, give me some indication of what the cumulative intermolecular forces are, because the phase change temperature is the energy I need to put in to overcome the intermolecular force. So at the very least, armed with Wikipedia, I do have a way to assess the intermolecular forces between two molecules. I just look at the boiling point or melting point. Questions or problems? Well, if you have like a giant molecule like, I don't know, DNA, right? Or some giant protein, yeah, they can get high enough, but for the most part, I mean, you're talking gigantic van der Waal interactions versus my ionic compounds are all generally small. But yeah, I mean, the van der Waal forces do keep scaling as you get bigger and bigger. But for the most part, if they're ionic, I mean, there's very few room temperature ionic compounds that aren't crystalline solids. Very few. In fact, if you want to make money, there's a market for liquid ionic compounds because they allow you to actually transfer charge and stir. You know, so there's people that just develop them, but they're relatively scarce because that force is so strong. Most ionic compounds are just, you know, melting point of, you know, 2000 degrees. Other issues? Stay warm. It gets warmer next week, I'm told.
Thank you.
Thank you.
Have a good weekend.
Yeah, you too.
Thank you.
Hey, Professor, I have a question.
Yep.
So sprint one, right? When do those